right. So we left off with the regression decision tree. I don't think I really explained this code much again, so I just want to come back to this and remind you that we're inputting for our root mean squared error the labels of our test and the prediction labels. So this tells us, this can estimate how far off we are. And here we're also giving it the same data, right? So that we can tell how much better is our model from the mean. Okay. So just wanted to kind of clarify those inputs because I didn't in the last one. And let's now get into the second part of this notebook, where instead of predicting max heart rate, let's predict whether a patient has heart disease or not. So we're going to be using the column diag instead of max heart rate. This is now our target variable. And we first just want to look at the distribution of how these are set up. So value counts, if you remember, really handy pandas function to count the unique values in a data frame or a series. So here we're counting that we have many patients with zero vessels constricted, which is great, and then several patients with more than one in each of these categories. It's very possible to do multi-class models where you're predicting multiple classes. It's much simpler to do binary models. And even when you're working in a multi-class model, oftentimes under the hood, it's actually doing like one versus all, the next one versus all. So like 0 versus 1, 2, 3, 4, 1 versus 0, 2, 3, 4, etc. So we want to simplify it by making it into just 0 or 1, making it into a binary response variable. So we'll do that in a moment. I am gonna first separate out target and features. And here I'm asking you to assign different names to them. So instead of labels and features, I want you to label them Y and X. This is another common convention that you'll see. It's useful for, since we've done another tree in this notebook, we don't want to just overwrite those necessarily. So this is helpful for distinguishing that now we're working on the classification model. So this is code again you will do, so you'll add a code block and write in your own code. But first here, I'm again just separating out the labels into Y, the features into X, and making sure that I'm dropping the column of interest, our diagnostic column. So let's take a look at Y and just make sure that all looks good. Whoops, I forgot to run this. Okay, so Y right now is 0 through 4, right? We still see that. We, again, would like to make it binary for simplification here. Um, and so here we're going to say that 0 means there's no vessels with 50% narrowing. 1 means at least one or more of the vessels have narrowed, which is going to be our indication of heart disease. Okay, so we want to transform these into just ones and zeros. Your next objective is to write code that converts all Y values that are greater than 1 to 1. And I said the NumPy where function is useful here. There are several other ways to do this. So if another way is more intuitive to you, as long as it comes out with the same thing, great. So I'm using where here to say wherever Y is greater than 1, put a 1. And whenever that is not the case, put a 0. So that's the way that this command works. And so now if I print Y again, it should just be zeros and ones, and I can confirm that that is the case. Okay, so awesome. Now we want to actually split up our testing and train data. And again, we still have our features and our labels as the input, but this time they're called X and Y. Okay. Um, so same test size, same random state. Again, the random state number doesn't really matter, but we're separating these into X train, X test. Those are our features, and Y train and Y test. Those are our labels. And so I want y'all here in question 8 to really think about these pre-processing steps that you work through and write out the steps that we've done so far just to get us ready for the machine learning pipeline. Because remember, a really common or just a really core goal of this course is to get this pipeline, this workflow down, right? We're not getting into all the nitty-gritty, but we are trying to really master this flow. So think about this flow a little bit and answer this question. There's another question here you'll need to add a text box for and answer for us. So next we're going to move on to actually making the decision tree, this time a classification tree, fitting our model and visualizing it and predicting and evaluating. The same workflow, again, remember. So here, instead of decision tree regressor, we have decision tree classifier. You can see as I'm hovering over it, the parameters that go into it here. It's always really useful to read the manuals, but they don't always make sense at first. So as you work through it, just keep practicing, look up certain things. So here we're calling this, instead of reg tree, it's not our regression tree, it's our classifier tree. So our model is going to be called CLF tree. And again, here we are adding in our training data, features, and labels to train the model in the second line. Here again, we are visualizing it with GraphWiz, GraphViz, and we have our tree. So take a second to look at this. So this looks kind of different than our regression tree. We have an extra line here, this Gini value. And we also have, for the value, no longer a number, but two numbers here. So let's talk about how this is different, right? So for one thing, classification trees and regression trees are just working on loss functions, right? You can't take the residuals, which is what goes into the loss function of regression, with a classification model, because it's not the difference between an actual number and a predicted number. It's class yes or no, right? So here we're using a loss function called a Gini index. You'll read more about him in the background. It's a terrible name because the person that it's named after was a Nazi. So sort of unbelievable that these terms are in use. I really hate to use them, except that when names become so common, that they're recognizable, right? Sometimes this is also called the purity value or impurity value. I really recommend doing the by hand exercise for module 3, which will sort of prompt you to work on this loss function like by hand, in a really simple example using the background video. So if you want to get deeper into the Gini index, how it works, that's a great place to be. You can still run this without necessarily knowing this. The Gini index basically tells us how mixed the classes are once we've split. So if the Gini value was 0, that would mean that like all the samples belong to one class and all belong to another one. Perfect split. If the Gini index is higher, this is saying there's more sort of just messiness. It's not splitting out very clearly. Okay, so that's what you're seeing in this tree for the Gini values. Like you can see, this one's 0.5. That's the maximum you can get for the Gini index. And so that means that, it's totally random in splitting on this value. So some of these are better than other. You can see some of these actually are very useful in lower values. The two values that we see in each of them tell us how many samples have been labeled as no heart disease, how many samples have been labeled as heart disease. So, and again, it's just the order, the index order of the labels. So for each of these, it's looking for which feature can best, using the Gini index, which of them best, most cleanly separates out the data. Then this is another subset of data. Then which feature best splits this set of data, and so on. And so once we get to the leaves, we still have predictions about how many are in each class if they are fitting into these conditions, right? Okay. So, just some written text that maybe will be helpful for that. This is our tree. And again, these values can kind of tell us what's important. Like here, that this is splitting on a thallium test. This may tell us that a thallium test is a really good indicator of whether someone, or a really good place to start at least, whether someone has heart disease or not. So you could even see a doctor, Is it a good idea to administer a thallium test first and then decide if you want to see the patient or not see the patient based on that value? Maybe so, right? So let's look at the thallium variable a little bit closer. So here we're using Seaborn to plant or to plot our data. And here on the x-axis, we're giving it the diagnostic category. And on, you'll see that we're coloring it by the thallium. So we're going to get 3 values for each of the diagnostic categories. We don't have to tell it the y-axis because it has the data and we specified that it should be a count plot. So it knows that its job is to count up the number of data points in each. So that's what we see here across these diagnostic categories. And here we've unsplit it, not looking at it binarily. But you can see that in the diagnostic category of 0, that's our no heart disease, we see a really strong pattern, excuse me, a thallium value around 3, right? And so if we're making these splits about, at what point, at what value of the thallium test are we going to be concerned about heart disease, this can tell us that if we have something higher than 3, we might really want to be concerned about heart disease. Excuse me. So I want you to reflect on this a little bit with this data, and that's your question 10. Oh, excuse me. Sorry about that. So again, we're thinking about interpretability. That's the strength of decision trees. We can see how the algorithm is thinking about this decision tree. We can also look closer at the variables that it uses higher up in the tree because those seem to be really important for trying to cleanly separate out patients into heart disease or not. And finally, we can make predictions, right? So let's predict here. We're using, again, the predict and the features test data, X test data. We wouldn't want to predict on the training data, right? We want to make sure our predictions are on the test data. And now let's look at the predictions it makes. So we saved it as Y preds. And then we want to look at the real values, Y test. So these are our predictions for each patient. These are our actual values. And we can look at these and line them up and see, okay, with my eyes, they look pretty similar. But it's more useful to actually count them up, right? So this is an easy way to do that using count non-zero. Count non-zero is going to count, like it says, how many elements are not 0. That's sort of funny because what I have in here is a logical statement. And maybe let me just print this above so that y'all can see what this looks like without anything else. This is a conditional saying, tell us true or false, logical, whether a sample is going to agree both as heart disease, right? So we see falses and trues. When we wrap that in count 0 counts trues as non-zero. So that's why the next part is actually going to give us the counts for our predictions. This is for the number of times, right, that the test predicted heart disease and it was actually heart disease. These are our true positives. You can see that there's 36 of them. That's useful, but it's even more useful to look at the whole kind of spread about your results. And as you saw last time, confusion matrices are great ways to do that. So again, remember that's from the sklearn metrics package. It has this confusion matrix command in it. We are inputting into it our tests and predictions and printing those here. Okay. And here we're actually giving it our tree itself. So in this, as we look at it, the lighter the color, the more there are, we can see that these are the true positives where the label is truly 0 and we predict 0, or the label is truly 1 and we predict 1. So our true positives here. And then we have other cases, right, where the true label is 1, but we predicted it as 0, so we missed it, right? False negative. Whereas this is a different case where we have predicted that it's going to be heart disease, but is actually not. right? False positives. And so I want y'all to, the next thing you're going to do is to actually calculate this using your own code. Um, I don't recommend, as I write here, to just hard code these numbers. I'm not asking you to just plug these into the formulas for each of these to get the proportion. I think trying to do it code-wise is much more productive for y'all. So again, here I'm using the count non-zero in the logical framework to try to find the false negatives, ones where the actual result is 1, but we predict it as 0, so we miss it. And then here I'm using the data shape um, to get the rows to take the proportion of them. So here about 2% of our data is false negatives. The next thing that you're going to be doing is to calculate safety and recall, or sorry, safety and efficiency. And sometimes you'll see these under other names, recall, specificity. You can read in the background a little bit more about those, but there's different ways to do this. Again, I don't recommend just hard coding in the numbers. Use count non-zero, or you can also use sum. There's different ways to do this. This works because they're binary arrays, right? And trues are counted as ones. Um, and so here we're calculating safety and recall and printing those. And I want you all to reflect a little bit about what these mean, especially in the context of this data, what it means to have these as metrics for our model. So the next thing that we're going to do is to think about the overall accuracy. And remember that we can do this because it's a classification model. Um, so we can input our test labels and our predictions from that and compute accuracy, the overall performance, about 80% accurate. Not too bad. So the last two questions are just asking you to reflect a little bit on things you learned today, and reflect on whether you think this kind of decision tree would be useful for your own work or for doctors in a hospital. Right? Because we can actually view this, and as you get into more complex models, you'll really appreciate the interpretability of this, that we can really see how it's making decisions, that we can find out some information about the biology behind them, and that we may actually be able to use them for decision trees we make in medical settings or biotech settings, right? So thanks for hanging in here. The next video, we are going to be testing other things about the layers of our tree to see when we, when we have really shallow trees that maybe don't learn well enough to make good predictions, or really deep trees that learn our data too well. So stick around for the Notebook 2B next time. Thanks, everybody.